Okay, hello everyone. I am Rong from the DAMO Academy in Alibaba Group. Today, I'm honored here to give this talk on our roadmap and the progress in the AI for DB field. As we all know, AI for DB has been becoming a hot research topic in recent years, both in academic and the industrial area. So in this talk, I will introducing our roadmap and the advances in each step in our AI for DB research. And in this uh, outline, our target is to design and implement an intelligent cloud DB from the existing traditional DBMS. We will start this journey step by step from the models, algorithms, frameworks, benchmarks, and the tools during this journey. So now start to enjoy the journey to an intelligent cloud DB with the advent of artificial intelligence. Okay, so the first problem to start this journey is how we start the first step in a very complex DBMS. We all know that there have been many different components with different functions in the DBMS. To select the first field is a very important initial step. To achieve this, we have analyzed and found that until now, by some survey, there are in fact four different directions in AI for DB research, including the work on the database configuration, such as knop turning, and query optimization, including cardinality estimation, join order selection, cost model, and the end-to-end optimizer. And there are also include the database design, such as the learned data structure, such as indexing and transaction management. And the other part is the database monitor, such as performance and the system diagnosis. So within them, I think that the query optimization has been the very important pivot field because it has provided the experimental tool for different machine learning techniques such as supervised learning, unsupervised learning, and reinforcement learning. And it involves both system and algorithm co-design, and the QO plays the most important role that directly relates to the system performance. So we select query optimization, this task, to be the first step to verify our design in the AI for DB techniques. For more details, please refer to our this tutorial, Learned Query Optimizer at the front of AI-driven databases in this year's EDBT. Okay, now let's start. For the query optimization and also many other AI for DB tasks, the first fundamental problem is how to accurately and compactly represent the data and query information, because this lays the very solid foundation for you how to achieve the algorithms. So this compact and accurate representation can play important roles to many different tasks, such as cardinality estimation, cost model, and indexing, and some other tasks. Okay, in our task, in fact, in the literature research, there are two ways to representing the data and the query model. One is the statistical model, such as histograms, kernels, SVMs. They are simple, compact, but maybe not very accurate because they use very rough and may not realistic assumptions. Another way is using some deep models, such as different types of DNNs. They are very accurate, but they may not faster in inference, and they are not explainable. So our focus would be another type of the models called probabilistic graphical model, such as the Bayesian network or the sum product network, or in short SPN, or our proposed new model FSPN. Okay, so the probabilistic graphical models, or in short PGMs, are a simple, compact, and they are also accurate and explainable models. So we focus on them. Our solution is to revitalizing these existing PGMs and trying to design new models. Okay, for on traditional PGMs such as Bayesian network, we make it more scalable and more efficient. We have proposed a more efficient and scalable structured learning for Bayesian networks in this paper, ICDE paper. And we also design a new PGM called FSPN. It subsumes all advantages of existing PGMs. You can refer more details to this paper. And it is as accurate as the Bayesian network and also as efficient as the SPN. And it is an explainable model. Okay, on top of these models, the next problem is how we design algorithms which is applicable for learned component functions in the DBMAs and QO. We choose the cardinality estimation as the first step task. Our principle and design choice is trying to design the algorithm by real-world requirements and examine it by real-world settings. For estimating the most simple selectivity, that is how many tuples of a subquery may access in the DB, we try to design an algorithm both efficient and accurate. We propose this flat algorithm published in VLDB, and they also propose this Bayes card algorithms, which using a Bayesian network. They achieve the total performance by end-to-end evaluation in real-world DBMAs. And another task is how to estimate the distinct values. We're trying to using this statistical model to learn estimate for the number of distinct values of queries. This work is also published in this year's VLDB. Okay, on top of the algorithms, the next problem is how to learn a complex modular. Well, here, a complex modular means that it may using different components to achieve a very complex task. Here, let's revisit the structure of the query optimizer. Its input is a data D that can be represented using our model. And it also, for input query Q, it try to generate a physical plan P to execution. The task of the QO is to find the most efficient plan P to execute for the query Q. In fact, the module QO modular may contain often contains three components: the cardinality estimation, try to estimate the cardinality of the query Q, of each subquery of Q, and then using a cost model to estimate the cost of executing this subquery, and a join order selection try to identify a suitable order of different joins that combine different subqueries to form the plan P for execution. Nowadays, there are many work trying to learn the end-to-end query optimizer, not to learn the whole query optimizer as a task. But a desirable learned E2E query optimizer have many challenges. First, we all know that cardinality may be not accurate, so it needs to tolerate the inaccurate cardinality. And try to deploy a learned query optimizer into a DBMS is a very hard task. So it should be easy to integrate and deploy in existing DBMS. And a learned task may have cold start and performance regression problems. That is, its performance may lower than the traditional one at the initial. So we should using some techniques to alleviate this cold start and performance regression problem. And a learned task should have the ability to generalize across different DBs, different data, different schema, and different workload. So it's a very challenging and difficult task. By us, we propose a learned QO framework for Cloud DB. We called it MTMLF. It's a unified transferable model for ML enhanced DBMS. We published this work in this year's CIDR as a vision paper. The main idea of this learned framework is that it contains two stages. We divided all knowledge into two parts. One is the data or task agnostic knowledge. We can learn this by pre-training models, which is provided by the service provider, such as cloud service provider. They're trying to pre-train a large models that has witnessing many workloads, many data that as a fundamental model that is applicable to different users. And then this another part of knowledge is the data or task specific knowledge, which is relevant to the users. So we could fine tuning and to refine this big model by user data. By turning it, it may become more specific and close to users' requirements in their applications. So it is generalizable across different DBs, tasks, data. Yes. So it achieves what we have designed for a desirable learned query optimizer. Okay, this is frameworks. We have designed algorithms and frameworks for the component level and modular level tasks. The next problem is how to revert the actual performance of these learned methods in the real-world applications. That is, how to design the benchmarks and do the performance evaluation. Well, for the benchmarkers, we summarize that there are three most important aspects for a good benchmark. First is the environment. It should be deployed in a real DBMS city to revert its performance in the real world city. Second is for the data and query workload. It should design to close to the real world cities. We know that TPC-H and TPC benchmark is well known because it's close to the real world requirements, query requirements. And the third part is how to design the metric. It should have a good metric to reflect the real performance. So environment, data and query, and metric are three most important aspects for a good benchmark. For query optimizer and canality estimation benchmark, we try to a lot of new work towards this direction. First, we design a new benchmark for canality estimation and query optimizer. We publish this paper, Canality Estimation in DBMS, a comprehensive benchmark evaluation in this year's VLDB. We also open source all this work, including the data and query workload we designed, and the tools and the metrics. And we also provided a method to integrate any cut-east algorithms into our framework. Within this benchmark, it contains a new dataset called status and a new query workload called status CEB. They are extracted from the real-world settings, and all the queries are generated by the real-world users' requirements. They are more complex and close to the real-world settings in comparison to the traditional work. And we provide a plug-in tool which can integrate any cut-east method, learned or traditional statistical method, into the PostgreSQL, this open source DBMS for end-to-end test. Because we think that the end-to-end execution time is the best and the golden standard metric to reflect the algorithm's performance. But the overall end-to-end time is hard to test. You need to run the whole workload. So we design a new metric called p-error, a new metric that is closer to revert the overall end-to-end time. But you do not need to run it. It can purely compute it offline, very convenient and distortionless. And you can use this metric to give a detailed analysis on the pros and cons of your designed canality estimation and query optimization learned algorithms. Okay. Having doing the benchmarks, we may take in hand some very good algorithms and frameworks. The next problem is how can we deploy these learned AI modulars into an existing DBMS? Yes, with minimum cost. Trying to deploy AI modulars into a DB is a very hard task because AI and DB are in fact a tale of two cities. For DB systems, we want to be stable and deterministic behaviors. But for AI models, they are often very unpredictable and have statistic behaviors. So we're summarizing some high-level requirements on the combination. First, the AI modulars need to be deployed to be separate from the core systems. So you do not need to disturb the normal service of the DBMS. And we need to have minimum third-party dependencies to ML training and inference libraries. And for the AI modulars, we should have general programming models to different tasks in the DBMS. And we need to consider the usability, configuration ability, robustness, stability, and fault tolerance. They are general requirements for the systems. To this end, we designed a new tool called 百合 for AI for DB system tool deployment. We have integrated system, the open source Postgres with any learned QO component using its hook materialism and implement our 百合. It's a general system framework for AI-driven databases. This is the general system architecture. We deploy the AI modulars in a training environment with some support library, and each model is run as a background services, and we use an extension from over the DB host system without modify its kernel systems to integrate and to communicate with these models. Okay. It will be open source soon as a general system tool for both industrial and academic research. Okay, here we summarizing our work from existing DBMS to the intelligent cloud DB. We still have many things to do, and our goal is to make AI truly workable and helpful in DBMS. We hope we could work together to achieve this goal with all us together. And we are also outline our future tasks to make each step from models, algorithms, frameworks, benchmarks, and tools more solid along this way. Thank you. This is my talk. Thank you.